Okay, we're going to look at something again that's familiar from chemistry, and it's something called the ideal gas law. And just to break this one down here, the ideal gas law looks something like this. If I look at the ideal gas law, it is written as, and I'm going to save time on deriving this, but essentially it is going to be equal to PV equals nRT. You may know that this is, this is going to be your pressure. This is going to be your volume. This is the moles. Hopefully you're familiar with that one. This is the temperature, and it's always in Kelvin. Okay, so make sure that's always in Kelvin. And this little guy here, big R, is called the gas constant. And for you, it'll be 8.314 joules per mole per Kelvin. And you may know this as a different constant, but for us, we'll have to know 8.314 because those are we're always going to be dealing with SI units. This has some interesting ramifications here, and it could be as follows here. Suppose we ask that what is the volume of 1 mole of gas at 1 atm. So at 1 atm. Well, for this one here, if you plug in your numbers here, and we maybe have to use SI units here, rather than 1 atm, maybe I would convert this into 101.3 kPa. And let's say here that this is at 0 degrees Celsius. It's kind of a useful thing here. So 1 mole of gas at 1 atm at 0 degrees Celsius. Well, if you plug in all your numbers from before into this formula, PV equals nRT, and you solve for the volume, volume, you're going to get nRT divided by P. I'll save you the time, but you're going to end up getting 22.4 liters. This is a useful result because notice I didn't specify what type of gas. It actually doesn't matter. Any gas at 1 mole of that gas at standard pressure and at 0 degrees Celsius, or that should be 0 degrees Celsius, is going to be 22.4 liters. This is actually 0 degrees Celsius at 1 atm is something called STP, which stands for standard temperature and pressure. Standard temperature and pressure. Okay. It's useful to note here from all those other laws you may have heard of, Charles' law, Boyle's law, is that if I move the equation around, PV divided by T, this is going to equal a constant. Again, moles we have really no control over. They're just sitting in like a balloon or the substance. But what this says here is that if this equals a constant, if the pressure goes up, in order for this to be a constant, then either the temperature has to go up or the volume has to go down. And they all obey this three-way relationship here. Usually one of these will be held constant, and of course as pressure goes up, then volume would have to go down, or as volume goes up, temperature has to go up, etc. And notice those relationships there. One last thing here is to look at alternative representations of the ideal gas law, and that is this. You could have PV is equal to, I'm going to write a capital N KB times T. Instead of writing nRT, this is a little bit different here. Capital N is going to be equal to the number of, instead of moles, it's going to be the number of molecules of the substance. KB is something called the Boltzmann constant. Okay, the Boltzmann constant, and it ends up being 1.38 times 10 to the negative 23 joules per Kelvin. Where this comes from is somewhat familiar here, and that KB is essentially equal to R over NA. And if you remember what this is, R is going to be equal to 8.314, and this is something called the Avogadro's number, which is going to be equal to 6.02 times 10 to the 23rd. And for anyone who's taken chemistry, that number is probably ingrained into your memory here. So you end up getting this just in terms of what KB and where it comes from. It's basically dividing by Avogadro's number. And of course, if I take moles and divide by Avogadro's number, it'll give me number of molecules anyways, or multiply, pardon me. And that's why they end up canceling each other out. So there's a little alternative formula that you may have to use as opposed to the one given before. One last thing here to talk about is talking about the kinetic molecular theory. Make sure you read up on the kinetic molecular theory in your textbook. It's very important to look at those points. I'm not going to write them down here, but please make sure you read up on all the points of the kinetic molecular theory once again. A couple things about the kinetic molecular theory is that in a gas, it turns out that the average kinetic energy of any molecule that's moving around there is going to be directly proportional to the temperature. This again is a constant. This is Boltzmann constant we just looked at, and 3/2 times that. But the temperature, as the temperature goes up, the average kinetic energy of the molecules tend to go up, which explains a lot of phenomena like increased pressure, decreased volume, all of that. Well, because of this, if this is the average kinetic energy, we could say here that this is also equal to 1/2 mv, and I'm going to call it V average squared. Okay, so the average kinetic energy can also be equal to this. When you move this around here, what you're ultimately going to get here is something called, and I'm just going to write it like this. If I take the square root of the, again, instead of writing V average squared, I'm going to put a little bar above this and just call it the square root of the average squares of this. It's kind of awkward to say here, but that's going to be equal to, well, after moving that around here, you're going to get here square root of 3 kb capital T over m. Again, this is all in Kelvin. So here's the mass of, let's say, each molecule here. It can also be written as 3 big RT over big M. And again, this is the molar mass. So you have molar mass or just the mass of the particle. So either one of these would be directly proportional. What this says here is that the average speed, it relates the average speed of a particle to the temperature. Sometimes this is referred to as VRMS, and it stands for root mean squared. In other words, the average mean, and you take the square root and then you square it again, of all of these particles.